All right. So here is your video for graphing tangent. So this is the last trig function that we'll graph together. So tangent looks and acts a little bit different than what we know about sine and cosine. Although it looks a little funkier, it's actually a little bit easier to graph than sine and cosine. So if you decided to print out the sheet that I posted for you, you'll see that I went ahead and copied a picture of the unit circle on here. And this is just to sort of make that connection between the unit circle and what we're going to be graphing here. So if you take a look here at our unit circle, what we know about tangent and in terms of its coordinate points is that our tangent of an angle is our y value over our x value when we're talking about these coordinate points here. So to look at this unit circle and figure out when we stack the y on top of the x here, places that are nice to graph, and when I say places that are nice to graph, I mean values that are nice to graph in terms of y values, we're going to look here at 0 and 1, 0. We're going to look here at pi over 2, we'll look here at pi, we'll look here at 3 pi over 2, and then we'll go ahead and we'll take a look, instead of graphing the square root of 3 over 2 like we have here, instead of graphing that, why don't we take a look at what happens when we put the square root of 2 over 2 divided by the square root of 2 over 2. So we're also going to go and take a look at all of these pi over 4 pieces. Our first value when we're graphing tangent, we're going to take a look at what negative pi over 2 would look like. And we're going to increase by these increments of pi over 4. So negative pi over 2, pi over 4. Then we're going to take a look at 0. We're going to take a look at pi over 4. We'll look at pi over 2. We'll look at 3 pi over 4. We'll go ahead and look at pi. We'll look at 5 pi over 4. And then we'll take a look at 3 pi over 2. And as we sort of graph this first chunk here of tangent, I think it will make a little bit more sense as to why we start in the negatives and not necessarily start at 0 like we do for our other functions. So thinking about at negative pi over 2, which we know is going to be the same thing as 3 pi over 2 down here. Negative pi over 2, if I were to do my x over my y, let's rewind that for a second. Here at negative pi over 2, if I were to do my y over my x, gosh, I just did it again. So negative 1 divided by 0, that's going to get me something that's undefined. So this is why tangent sort of looks and behaves a little bit different than our other trig functions, because there are values where tangent is undefined. If I then come over here, 7 pi over 4 acts the same as negative pi over 4. Negative square root of 2 over 2 over square root of 2 over 2. That's going to go ahead and put me at negative 1. At 0, I'll have 0 over 1, which is 0. At pi over 4, positive 1. At pi over 2, I'm again undefined. 3 pi over 4, I'll be back down at negative 1. At pi, again, I'll be at 0. At 5 pi over 4 over here, negative divided by a negative is going to put me at positive 1. And at 3 pi over 2, I'm back where I started with at negative pi over 2, and I know I'll be undefined. So when we're undefined, we're just going to go ahead and sketch in an asymptote in those places. So I have negative pi over 2, I'll have an asymptote, and positive pi over 2. So the way that we're going to go ahead and graph this, and it'll be a really similar pattern each time, is I'm going to go ahead and my in-between value, so in between pi over 2 and negative pi over 2 is always, I don't want my highlighter, is always where my sine graph is here at 0. And if I look exactly halfway in between my in-between, so if we're taking a look here, so in between where I'm at 0 and in between where my next asymptote is, I'm going to be up here. Let's say this is 1 and -1. I'm going to be up here at 1, and my other in-between, so that negative pi over 4, I'll be at -1. And sketching in what this graph looks like, it's just going to swoop and follow where those asymptotes are. So looking here at 3 pi over 2, in the middle I'm at 0, in the middle, so 3/4 of the way and 1/4 of the way. And my sine graph is just going to keep repeating and repeating just like this. So we can definitely see how this behaves a little bit different than my regular sine and cosine. So getting rid of this unit circle, I'll uncover some pieces here. Let's erase my scrap work. I'll uncover some pieces here. So tangent always has asymptotes at -pi over 2 and pi over 2. But remember, when we have those bx minus c shifts, those take into account where my tangent's asymptotes are. So what will happen here is, in order to find my asymptotes, I can set bx minus c equal to -pi over 2 and pi over 2, and that will tell me where my asymptotes occur. Then the x-intercept is always exactly halfway between those two asymptotes, and halfway in between here, I'm going to be up where, so in this case we were at 1 because the amplitude was 1, but if my amplitude was something like 4, this would be up here at +4, and my halfway would be down here at -4. So let's go ahead and let's do a few of these examples together. So looking here, I'm going to take my bx minus c and set it equal to -pi over 2, and my bx minus c and set it equal to pi over 2 to figure out where my asymptotes will be. So I'm going to take 1/2 x and set it equal to -pi over 2. And to solve this, I'll multiply both sides by 2. So I get x is equal to -2 pi over 2, or -pi. So that happens to be where my first asymptote is located. My next asymptote will be at 1/2 x is equal to pi over 2. So I can multiply both sides by 2 here and get that x is equal to 2 pi over 2, or x is equal to pi. So I can come over here, and there's my pi. So exactly halfway in between is going to be my x-intercept. I can see that my amplitude here is 2, so exactly halfway in between here, I'll be up at 2, and exactly in between, I'll be down at 2. And so then I can go ahead and sketch in what this function will look like. So from -pi to pi, I will have 1 full period of this tangent graph. So let's go ahead and do another one together. So I'm going to take my x plus pi over 4 and set it equal to -pi over 2, and x plus pi over 4 and set it equal to pi over 2. So I'm just going to go ahead, I'll zoom in here so I can solve. I'm going to subtract pi over 4 from both sides. So x is equal to let's call this 2 pi over 4 minus pi over 4, making a common denominator, minus here. And so I'm going to end up getting -3 pi over 4. So -3 pi over 4 is going to be in between -pi over 2 and -pi. And over here, I will add pi over 4 to each side. So I'll get x is equal to 2 pi over 4 plus pi over 4. So x is equal to, excuse me, let's back up. I should be subtracting here, excuse me. minus pi over 4 from both sides. So here I'm subtracting, and I'm left here with just pi over 4. So here at pi over 4 is another rotation. So exactly halfway in between negative 3 pi over 4 and pi over 4, I can see that I am here at negative pi over 4, and my amplitude here is just going to be 1. So I'm up here at 1, and I'm down here at negative 1, and I can sketch in what this graph would behave like. So I can go ahead and sketch in another period of this function. So I would be here, here, and here, and another asymptote. So you can just keep sketching in periods of what this function would look like. So there's graphing tangent. So big takeaway here, guys, is this piece here. So to keep finding that bx minus c, setting it equal to negative pi over 2 and pi over 2, and then finding my 3 coordinate points here. And again, it ends up acting, for a technical term here, we could call it swoopy if you would like. Swoopy in between there. So another way to do this is certainly to go back and plug in my x values and evaluate, especially if we have some negatives that are flipped in here, makes my graph behave a little bit different. So you do have some other tangent practice, not on this problem set necessarily, but for homework. So I encourage you to make a table, and certainly please show your work in finding where the asymptotes are located. Good luck, guys.